Good morning, everybody. So today we are having the lecture on FinFET design. Basic thing, whenever we switch to another technology or we switch to another transistor design, we have to first look why we are switching towards the next design. What are the disadvantages which are associated with the previous design? So first of all, we just try to find out why we have to switch to FinFET. What are the shortcomings there with the MOSFET design? So why FinFET? That is the first question that comes in our mind. So before we move on to discuss process technology and the manufacturing of FinFET and tri-gate transistors, we need to get brief motivation why there is a need of tri-gate or FinFET or gate-all-around or FD-SOI kind of devices. So what is the need to move from planar MOSFET structure to FinFET? If we just look towards the normal MOSFET design, so in normal MOSFET design, you can see that there is a P-type substrate, two source and drain regions are there. So, and they are basically N plus regions. So we can think of there is the band diagram, and in band diagram, we are making NPN structure. So if we just try to find out what will happen if we apply some gate voltage. So whenever we gate voltage will be applied, the electrons which are present in bulk will be attracted towards the channel. And because of that, as we are increasing the gate voltage, the channel formation will be there. It means more and more electrons will move towards the interface, and channel will be created. Now, when we apply some drain voltage, because of the application of drain voltage, there will be the conduction of current, conduction of the carriers from source to drain region. It means in P-type of PMOS or NMOS, both of the sides, you can think of carrier movement is there only from the source to the drain movement. So basic thing is there that if we are talking about the current, it means there should be the movement of the carriers from source to the drain. If suppose carriers are coming from the substrate to the drain or substrate to the source, then we cannot call it as a current conduction. Current conduction means the charge carriers are moving from the source to the drain. So in long channel MOSFET, basically we talk about as we are increasing the gate voltage, channel formation will be there. But as we are increasing the drain voltage, if suppose gate voltage is absent, channel is absent, then obviously there will not be any current conduction. So you can see that the barrier will be shifting, or you can say reduces as we apply the gate voltage. But it is not basically because of the drain voltage. It means drain voltage, if we are increasing, then there is no change in the barrier potential. So in long channel MOSFET, if drain current increases, suppose if we draw a ID versus VGS curve, then we can see there will be some exponential region as well as some linear region. So linear region, we can call there is some subthreshold slope. So if suppose we are changing the drain voltage, then obviously the current is increasing. So in long channel MOSFET, if drain current increases n times, then there is a n times increase in the drain current in off and on state. So you can think also that the subthreshold slope also remains same. It means the whole of the curve will be shifted upward without any significant change. Same off current will be there, same on current will be there, and same subthreshold slope will be there. So in long channel MOSFET, you can think of the characteristic is like threshold voltage remains same, it is not changing. Subthreshold slope remains same. On and off current increases with the drain voltage in same proportion. Now we talk about the short channel MOSFET. So in short channel MOSFET, if suppose we have the drain voltage of around 10 millivolts, things are same for long channel as for long channel MOSFET, and barrier lowers only with the gate voltage. So if we are changing the drain voltage with a small proportion around 10 millivolts, then the barrier is not changing. Barrier will remain same. But if we talk about the high drain voltage application, so barrier also lowers with the applied drain voltage. It means along with the gate voltage, the barrier is lowering with the drain voltage also. And that is basically creating the problem, because we do not want, if suppose VGS is 0, if suppose gate voltage is off, then in off state there should not be any current. But because of smaller channel, if we apply some drain voltage, still there is a current. So that basically current may be considered as leakage current, and that is undesirable characteristic. It means barrier for electrons to flow from source to drain is not only affected by the gate voltage but also by the drain voltage, and basically this thing is undesirable. And also, if we just look towards the curve, if suppose we talk about that we have increased again the drain voltage by 100 times, the on current is changing with the same proportion. It means if it is changed, drain voltage is changed by 100 times, then on current will also change by 100 times. But other than that, the sub-threshold slope as well as the off current, they are changing in different proportion. So if suppose we say that when VD was 10 millivolt and sub-threshold was around 90 millivolt per decade, and when we change it to 1 volt, the sub-threshold slope changes to 120 millivolt per decade. Also, the off current is also changing more than 100 times. So if you just try to find out the threshold voltage point, that threshold voltage point is also shifted. Earlier maybe it is positive, after that it may be negative. It means suppose earlier it was at 0.1 volt and now it is shifted to minus 0.05 volt. So there may be some change in the threshold voltage, and that change is around 0.15 volt. So in short channel MOSFET, if drain voltage is increased 100 times, then on current increases 100 times, but off current increases even more than 100 times because of decrease in barrier at higher drain voltages. Along with that, the threshold voltage also shifts with the application of drain voltage. So if we summarize the things, we can say that there is some DIBL effect, that is drain induced barrier lowering. It means barrier is lowering because of the application of the drain voltage also. The sub-threshold slope is changing, as well as the off current is increasing. Off current increasing means we are saying that the leakage current is increasing. So what are the possible options if we do not want such kind of undesirable characteristic? So what are the options? So all these short channel effects are bad for the devices and the circuit, and all these effects are lowering the gate control over the current flow. So if we can add more gate. Okay. So if we can add more gate, one above and one below, then you can think of we'll have more control over the gate current. It means suppose we are saying that the VGS is off, it means there should not be any channel. And when we are talking about VGS is on, so in both of the cases, if suppose the gate region is from both of the sides, then more control will be there with the electrostatics. It means more more controlled current will flow. So if we can add more gate, one above and one below, for example, double gate MOSFET, or put another gate at the side also, that is tri-gate MOSFET, or put gate all around, that is gate all around, then control over the current flow can be increased. So the researchers started thinking of that if suppose we can have more control over the electrostatics, then why don't we switch over to that? It means now if we talk about current technology, basically nowadays Intel is fabricating the different circuits based on FinFET devices or tri-gate devices beyond 22 nanometers. So the difference between FinFET tri-gate device is that in FinFET device we have only 2 gates and we don't use top surface as gate. That is, top surface have a thin silicon nitride layer. So from the top there is no effect on the channel, but from the sides only. While on the tri-gate devices there is the control from 3 sides of the channel. So Intel and TSMC announced that they will be using tri-gate device beyond 22 nanometer technology, but there are also some foundries still exploring FD SOIs, fully depleted SOI devices. To use it in further future. So FD-SOI is still an option to fabricate mass transistor, but as we see, the big giant Intel is using Tri-Gate. The FinFET technology market is estimated to reach up to 32.74 billion by 2022 at the CAGR report of 28.6% growth through the forecast period. So this growth in FinFET technology market is due to the increasing IC industry, which is providing ample growth opportunity to the FinFET technology market. So you can just visualize the curve. In that curve, you can see that with the same parameters and the voltages applied, the gate voltage and channel current, you can see when VGS is 0, in planar MOSFET still there is a current, while in Tri-Gate devices current is almost 0. So you can think of some shifting of the subthreshold slope, some DIBL effect is there, and because of that we are getting better option in the case of Tri-Gate. So Tri-Gate basically decreases off current and it provides a better subthreshold slope. Now we talk about the FinFET device. So basically in fin, we talk about basically the fin is grown over the surface of the wafer, and then we cover it with the gate. So you can think of, if it is a double gate structure, the side of the fins, we apply voltage from the side of the fins, but top surface is not affecting the channel. It means the application of voltage on that side is not affecting the channel, and that is because we are using some silicon nitride at the top, and that is inhibiting that voltage to affect the channel. While on the Tri-Gate structure, we will have a gate or covering the 3 sides of the fin, and we can have the 2 possibilities, 90-degree corner and half circle corner. We'll see later on why these 2 configurations are not good or advantageous, because of some corner effect in the 90-degree corner, and if we reduce the half circle, try to use the half circle corner, then in that case the crystalline structure is changing along with the width. So now if we just talk about the schematic view of the double gate MOSFET, in basically simulation procedure we require this FinFET structure. Now the Cadence is providing that FinFET is already there in Cadence, but earlier when this thing was proposed in the paper, then researchers started thinking of how we can use this structure, how we can model it. So it is basically modeled as that there is a channel, 2 sides there is a source and drain, and on the top and bottom there is a gate, and gate is basically defining what will be the channel length. So 2D schematic view of symmetric double gate MOSFET is shown here. So fin design consideration, basically if you are talking about a fin, basically it will have some channel length, it will have some height, also it will have some width. So what is the effect of width and the height on the basic characteristic of the device? So if we talk about fin width, basically it is going to determine the DIBL effect. So can anyone tell me how this is possible? It means how the width is controlling the DIBL effect. If suppose we reduce this width, what will happen? DIBL effect will increase or decrease? So if suppose we decrease the width of the fin, what will happen? We will get more control over the gate, control over the current. So if we will have more control over the current, obviously the DIBL effect will reduce. Now next is fin height. If suppose we increase or decrease the fin height, so basically if we increase the fin height, obviously we are getting more space for the channel and more current can flow, more current density can be there. But basically it is limited by etching technology, because first of all we take wafer and then we start etching from all other side, and the fin will be created. So etching process will be more if we have more height. So we should have somewhere trade-off between the layout efficiency and the design flexibility. Another thing is fin pitch. So basically it is nothing but the distance between the 2 fins in the wafer side. So it basically it is determined by the layout area and limits source drain implant tilt angle. We'll discuss later on that this is also a problem, that if suppose fin is there and if we have to dope that fin with particular dopant, so the nearby fins are basically creating the hindrance, and there should be again trade-off between the performance versus layout efficiency. So if we talk about the FinFET modeling and the earlier MOSFET modeling, the basic thing is there that the equation of the current voltage relation and everything almost they are same. Only the thing that is going to change, that is the VTH, because if we just look towards the curve, that curve is almost same, except it is basically having the off current. So off current is reduced, and you can think of the threshold voltage is changed. So various parameters are indicated in this figure with the 3D type of view of this FinFET. So if we talk about, there are basically two effects: short channel effect as well as width effect. If width is narrowed or the channel is shortened, then this whole VTH is depending on this. So delta VTH, it means change in the threshold voltage, is basically depending on this minus Q NB, whereas NB is the bulk carrier concentration, then depletion width, which is nothing but basically equal to the fin width divided by 2 divided by oxide capacitance, is in bracket there is XHS plus XHD, which you can also talk about that this is also a charge sharing length, that is indicated XH is equal to XHS plus XHD divided by 2. So overall the threshold voltage of the short channel effect will be, if we compare with the earlier conventional planar MOSFET, then it can be written as VFB plus twice psi B. And these two basically effects, if you remember, one is their flat band condition and another is their contact potential. And because of these two parameters were added in the threshold voltage equation in MOSFET also. So it will be VFB plus twice psi B plus QNB into X depletion divided by COX into 1 minus XH upon LC. So LC will basically, it is a channel length, effective channel length, and that is indicated that LC is equal to L minus twice XM. So now next is narrow width effect. If suppose width is changing, then what will be effect on this threshold voltage? So various parameters are indicated in the figure, and from that parameter the equation comes out to be delta VTH is equal to NWE, it means narrow width effect, is equal to QNB X depletion divided by COX into pi DF divided by 4 HG. HG is the gate height. So on that basis, also the XDF is denoted as VTHS 8 epsilon X divided by pi square X depletion QNB ln 1 plus T gate upon T oxide. So overall, if you just look towards, there are two basic threshold voltage considerations. One is short channel effect and another is narrow width effect. So we both of the parameters, if they are changing, the threshold voltage is also changing. So if we talk about the layout, it means it may appear that we are switching from MOSFET design to the layout FinFET design. We are very much comfortable with the MOSFET layout. So we always think of that if suppose we have to change to another type of structure, then obviously layout is becoming very tough. So no, it is not that. Layout is almost similar to that of conventional MOSFET. You can see from the figure the layout of bulk silicon MOSFET and FinFET. So layout are almost same, except that the channel width is now quantized. It is not all through same, it is quantized. So now we have to switch to the two types of technologies which are basically used to make FinFET. One is bulk FinFET, another is SOI FinFET. Just imagine the condition that there are two conditions. You have a wafer, then you just starting etching of the wafer and then creating the whole fin, and basically, and then you are depositing on board. We'll see later on the fabrication step also, and we'll clear about this thing. But before moving to the these two differences, we have to clear what is the difference between bulk FinFET and SOI FinFET. So in bulk FinFET, basically the fin is starting from the wafer, and then it is moving, and beside that there is some SiO2, and after that gate oxide material is deposited over it. But while in SOI FinFET, the fin is starting from the oxide surface, and then gate oxide material is there. It means in SOI FinFET, the bulk and fin, they are not directly connected. So there are the two figures based on 22 nanometer technology. So 25 nanometer is the width of the fin, and 67 nanometer is the height of the fin in case of SOI FinFET. And in case of bulk FinFET, the height of the fin is 65 nanometer and 26 nanometer is the width of fin. So device engineers around the world are struggling to make FinFET on SOI substrate or on bulk substrate. So fin height is basically determined by the silicon thickness. So variation in the fin height and thickness is less in SOI FinFET than bulk FinFET. That is clear from the figure. But from the view of economics, bulk FinFET are cheaper than SOI FinFET. So the first paper on bulk FinFET and FDSOI by Hashimoto et al. Published in 1990, he used SOI surface and patterned the silicon in the shape of fin over the oxide surface. While Intel announced that in 2012 that they are going to use a bulk substrate to create bulk FinFET, and they used to define taller fins. So when we operate FinFET device like a microprocessor at very high frequencies, heat will generate in the fins. This is very common thing. You can think of that whenever we are applying some voltages, current is flowing through the fins, then heat will be dissipated, heat will generate. So there is a major scenario that, or major concern is how we can dissipate this thing, dissipate this heat so that the device will not affect later on. So since silicon is a decent conductor of heat and oxide has 100 times less thermal conductivity, bulk FinFET provide better heat dissipation. I hope you agree with this, because in bulk FinFET, fin is connected with the wafer, with the silicon bulk, while in the case of SOI, it is not connected. It is just over the surface of the oxide surface. So dissipation of heat or distribution of heat will be better in the case of bulk FinFET. In FinFET device, gate is wrapping all around the fins and controls current effectively. But in bulk FinFET, source and drains are connected through bulk silicon underneath and form parasitic NPN BJT. Basically, this is a 3D type of scenario that you have to imagine that from the two sides, source and drain is there, and fin is also there. So fin and source and drain, they are basically connected underneath with the same bulk. So they are going to form some parasitic type of element, parasitic NPN BJT, and some parasitic current can also flow underneath, which is not possible in the case of SOI FinFET. So we have seen one advantage of bulk FinFET and then another advantage of SOI. So this problem of bulk FinFET can be reduced by increasing the doping of bulk area, and which helps in removing this parasitic BJT of the IOF, but it adds process complexity. Now the last point which is against SOI FinFET in bulk, that is in bulk FinFET, to create source and drain region, some part of fin is etched at the ends, and source and drain region are easily created over the bulk silicon. You can just imagine that if you just look towards this figure, in bulk FinFET, if you just take this thing or imagine this thing, in bulk FinFET, the fin is connected with the source, with the substrate, or you can say the bulk. So if we just etch from two sides, so we will get some area to develop the source and the drain region. It means we can deposit some more silicon from those two sides, and we can have the better possibility to create source and drain region. While in the case of SOI FinFET, if suppose we etch from from the two sides of the SOI surface, we will not get the silicon to grow up with. We are getting only the oxide surface. So growing up of or developing source and drain region in case of SOI FinFET is difficult in case of SOI. So while in SOI FinFET, when some part of fin is etched to grow source and drain region, there is no silicon template to left underneath to grow. So basically, if you just suppose compare the SOI FinFET with the bulk FinFET, we are having different parameters. So in case of SOI FinFET, fin height is less, while in bulk FinFET, fin height is more. Cost of SOI FinFET is more, while cost of bulk FinFET is less, and that is because of the reasons we have seen that we are not getting the template, we are not getting the proper alignment. Heat dissipation is poor in SOI, but better in bulk FinFET. Parasitic BJT formation is not there in SOI FinFET, but it is there in bulk FinFET. Source to drain epitaxy is complex in the case of SOI, but very much easier in the case of bulk FinFET. So you can think of why Intel selected SOI bulk FinFET for the next generation beyond 22 nanometer. So if we just look towards the curve, DIBL effect with the gate length. So as the technology is advancing, the effective gate length is decreasing. And because of that, it is obvious that if gate length is decreasing, the DIBL effect is becoming more prominent. But FinFET is giving you the better option. So we are switching towards the FinFET, then Tri-Gate, and then gate all around. So as from the graph, it is clear that DIBL effect is less in bulk FinFET than SOI FinFET, marginally though, but it is obvious. But suppose if it is less, if we talk about the power dissipation of one transistor, and if we can decrease the power dissipation of one transistor, you can think, imagine what drastic change will be there in the power dissipation in a whole chip where millions of the transistors are there. So if we can reduce slightly, that will be effective. So DIBL effect is less in bulk FinFET than SOI FinFET as the effective channel length approaches below 50 nanometer. So now we just move towards the process flow of bulk FinFET, how that is created. So first of all, there is a wafer substrate, and over that substrate we produce some hard mask, and some photoresist material will be deposited over it, and then we start etching. So basis of FinFET is lightly p-doped substrate with hard mask on top as well as patterned resist layer. Then after the etching, we'll have this scenario. It means the fins are formed in a highly anisotropic etch process. Since there is no stop layer on a bulk wafer as it is on SOI, so the etch process has to be time based. You can just imagine that in case of SOI, we had the surface, and whenever the etching process reaches to that oxide surface, it will stop. But in case of this wafer, when we are etching from both of the sides of the fin, we are not having any stop implant, or we are not having any stop layer. So in that case, we should time this thing. We should have the timed process that after this time, theoretically, we can calculate that after this time, this much amount of fin width or fin height will be achieved. After that, we have to stop this process. So in a 22 nanometer process, the width of the fins might be 10 to 15 nanometer, and the height would ideally be twice that of more. Next is we deposit oxide layer around the fins. So oxide deposition will be there to isolate the fins from each other. Oxide deposition with a high aspect ratio filling behavior is needed. So we all know that for separation, oxide layer, if suppose we are using the oxide for separation, for providing the isolation, that oxide layer may not be very good quality, but oxide layer which we are using for the gate oxide deposition, that gate oxide material has to be very highly pure material. So next, the top surface, top of the oxide layer will be removed, and planar surface will be provided. So the oxide is planarized by chemical mechanical polishing, and the hard mask acts as a stop layer. Now bulk FinFET flow. If we talk about next process, that is recess etch. So another etch process is needed to recess the oxide film to form a lateral isolation of the fin. It means now you can see the fin is visualized from over the surface, and after that we have to deposit the gate oxide. So gate oxide is obviously, if we talk about gate oxide material, that has to be very pure material. So on top of the fins, the gate oxide is deposited via thermal oxidation to isolate the channel from the gate electrode. Since the fins are still concerned underneath the oxide, a high dose angle implant at the base of the fin creates a dopant junction and completes the isolation. So after that, there will be the deposition of the gate all around around this fin, and finally a highly N+ doped polysilicon layer is deposited on top of the fins. Thus, up to 3 gates are wrapped around the channel, one on each side of the fin, and depending on the thickness of the gate oxide on top, a third gate above. Depending upon whether we want to use the top surface for the conduction, for the controlling behavior of the gate, it depends. If you want to create the 2D device, then on the top the silicon nitride will you just see this hard mask. If that hard mask is still there, or you can say if you remove it and deposit the silicon nitride over it, and then this process is continued, then you can think of top surface will be isolated, and the top surface will not provide any gate controlling action. So that will be a 2D FinFET. And if suppose the top surface is also included, is also providing the controlling behavior, then this is basically, you can think of it as a tri-gate. So overall, if you just look towards the bulk FinFET flow, the influence of the top gate can also be inhibited by the deposition of a nitride layer on the top of the channel that I told you. Since there is an oxide layer on an SOI wafer, the channels are isolated from each other anyway. In addition, the etch process of the fins is simplified, as the process can be stopped on the oxide easily. So this is overall the bulk FinFET flow, that we had the substrate, then hard mask, photoresist, then etching process, then oxide deposition, and then this fin and gate creation. Similarly, you can think of there is a SOI FinFET flow. So in SOI FinFET flow, basically we have the substrate. Over that, the oxide material is deposited, and then silicon layer is there, and then we provide some hard mask over it, and photoresist material is deposited, and then we go for the etching process. So you can just visualize that the 2 fins are created, but both of the fins, or those fins, are basically not connected to the silicon substrate. So this kind of architecture is termed as silicon on insulator FinFET flow. And in that case, you can think of whole of the device is over the oxide material. It is not nothing connected with the silicon substrate. Now we talk about the process challenges. What are the FinFET process challenges? So everything we do to enhance scaling in the present day scenario involves a lot of compromises in device level. If any center is having any question up to this point, can ask. Is there anybody who have any query regarding the lecture up to this point? Can ask. Okay. So everything we do to enhance scaling in the present day scenario involves a lot of compromises in device level. So here we will discuss about the issues in processing point of view in making a FinFET or 3D transistors. So FinFET or 3D devices involve edges and corners to transport charges, and this brings a lot of challenges. The gate dielectric wraps around the fins, so it has to be conformal. Similarly, gate metal has to be conformal, and a lot of process challenges are related with the conformality of the gate material. Similarly, when we make source and drain region, that metal also should be conformal around source and drain region. So there are many process challenges which, but we'll talk about only few process challenges that are related with the 3D nature of the FinFET device. So first is the corner effect. If suppose we recall our study of the physics, so whenever we have a constant surface potential, the electric field is amplified at the corners as well as also in edges. It means if we talk about the current density, proper current density in the fin, then current density will be more on the corners, and also it will be more towards the edges, but it will be it is basically highly affecting at the corners. So just imagine that you have applied some voltage, some gate voltage is applied, and that gate voltage is around threshold voltage, and because of the heavy intensity of electric field towards the corner, you can think of that still some current is flowing through that corner region along the fin, which is undesirable. So we have a much larger electric field at the corners. Same phenomena applies to the fins, such that as we apply gate voltage, more electric field at the corners, and because of that much larger population of electrons at the corners as compared to the side walls. So if we plot current density at gate voltage near threshold voltage, then we find that due to higher population of electrons at the corners, the current is still conducting, which is bad for the FinFET, which is not a desirable characteristic, because we do not want that if the voltage, gate voltage is slightly comparable or less than the threshold voltage, devices is still conducting, because we want to have the FinFET act as a switch. When VGS is less than threshold voltage, then device should turn off, and when it is more than gate voltage, around VDD, it is on voltage is there, so it should be turn on. But turning on is not our problem. Problem is that off current. So if even the gate voltage is less than the threshold voltage, if suppose still current is conducting, that is a problem for us. So because of corner effect, device turns on even at gate voltage lower than the threshold voltage, and in turn we can say it reversely also, that threshold voltage decreases because of the corners. It means how we are defining the threshold voltage, we are defining like that threshold voltage is that voltage point at which the device turns on. So in turn we can say that threshold voltage decreases because of the corners. So if just we try to find out the effect of it, we can see the curve. So it is again ID versus VGS curve. So you can see that planar MOSFET is there, and FinFET with corner and edge effects. And then if all these are controlled, then what should be the FinFET actual FinFET ID versus VGS curve? So actually it has to be the off current has to be minimum, but because of the corner and edge effect, the I of current is slightly higher, though it is less than the planar MOSFET, but still that is the problem in FinFET device, because if we suppose move further, if we advance the technology, then this thing is going to be very much critical if this corner effect and edge effect is there. So unique advantage of making FinFET was its sub-threshold slope. Now because of corner and edge effects, the sub-threshold slope degrades, as well as we will have multiple VT points. So how do we remove this corner effect? How we can compensate this problem? So earlier we can see that there is a 90-degree corner in the fins. So one way to solve this problem is to round off the top surface of the fin. So take the fin and anneal in hydrogen environment. So hydrogen anneals and tends to round off the upper surface. So another option is to take a tapered fin, and you don't get any corners at the top. So two options are there, that we are rounding the top surface, or we are taking the tapered fin, so that we are not getting any corner in whole of the fin width. So we have the in fins. Earlier, if we talk about earlier, we have the constant bit, but now if we are processing towards this thing, we are changing the top surface as well as the tapered pin is there. So because of that, what will happen? The width is also changing along the fin, and that is also going to pose the problem, because the threshold voltage of the device as well as some other parameters are basically depending upon this width parameter. So if this width is constantly changing along the height of the fin, obviously that is creating the problem. So device threshold voltage as well as electrostatics are very much sensitive to width of the fins. So having multiple width are not good options. Also, when we are rounding or tapering the pin, then we are not getting the same type of crystalline plane all along the fin surface, and that is also a problem. Another option is that if suppose we cover the top surface with the silicon nitride, it means you can think of from the top we are not applying any gate voltage. Gate voltage is only applied through the side walls of the fin. So if we use thick nitride at the top and wrap gate oxide all around over the fin, then we are actually not using top surface, and corner effect will be minimum. And this is ideal 2D device, or you can say the FinFET device. All these are different approaches to avoid the corner effect. Another option is shadowing. If suppose we have a series of fins over the surface of the wafer, so how we have created the fins? We have basically etched the upper surface and created the different fins. Now the point is that fin is to be doped such that it should act like a channel. So if suppose we have to dope this fin area, how we can dope it? It means if you want the uniform doping all around the fins, then the dopant material should flow from all the direction to the fin. Then only we can have the uniform doping of the fins. So if suppose we talk about there are some N-type fins and P-type fins, and they are in the near vicinity. So when we are creating heavily doped source and drain region in the planar transistors, we require halo implant or source to drain extension implant. But problem comes if we from its 3D nature of the fin. So when we are creating fin, we need to dope the fin with the required concentration of dopant, and we require uniform dopant concentration in the fin. But because of the shadowing, because of the nearby fins, we do need to flow the dopant from all the direction, but in reality there are multiple fins created over the surface of the wafer, and some are N-type and P-type. So when we are creating P-type fins, we need to cover N-type fin so that their density or dopant concentration should not change, and because of that they are acting like a shadow. It means because of them the dopant is not possible to flow from all the directions, and when we are passing the dopant over the surface, it is not penetrating equally from all the directions, and this is termed as shadowing concept. So this is the basic process flow problem. So if we summarize the whole of the lecture, we can say the FinFET was originally developed for manufacture of self-aligned double gate MOSFETs to address the need for improved gate control to suppress eye-off current, DIBL, and process-induced variability for gate length less than 25 nanometer. Tri-gate and bulk variation of the FinFET have been developed to improve manufacturability and the cost, and it has taken around 10 years to bring 3D transistors into volume. If you just recall, basically the paper was presented in 90s, but all along more than 10 years required to take this thing into the reality. Multi-gate MOSFETs provide a pathway to achieve lower power and improved performance. And further evolution of the MOSFET is to a stacked channel structure may occur by the end of the roadmap. Thank you. If you have any question, anybody is having the question, they can ask.